Hello, this is Ms. Nichols, and this video is in our electrostatics unit. The topic is the electric field. And the essential question is, how do objects communicate their fundamental properties without touching each other, specifically the fundamental property of charge? So in the world of forces, forces are usually broken into two categories. One category is called contact forces, when things are touching each other, like friction and tension, those kinds of things. And then we have another category of forces called non-contact forces. Forces like gravitation and the electric force and magnetism, which we'll learn about later on, are non-contact forces, which means that they can act through space on other objects. Even if they're not touching, even if there's a vacuum between them. And that probably makes sense when you think about how gravity works on objects in space, or if you've played with magnets before, you know that they can attract and repel each other through space. How exactly non-contact forces work is like cutting-edge research in physics. And maybe some of you will go on to answer those questions for us a little bit better someday. But we think that fundamentally these properties of charge and mass, etc., somehow change the fabric of space-time around them. And I'm not going to define fabric of space-time for you right now. I tend to think of them as kind of like a stink or a smell. They spread this little smell out, and it somehow changes the space in the region around them. You may have seen pictures before of how gravitation can be viewed as kind of a warp in the fabric of space-time. Now, space-time doesn't actually look like this. This is a model, but you can tell that the different sizes of objects create different warpage or wells in the space-time continuum around them. And you should know that we think the same general principle holds for all the forces. There's just a different kind of warping in the space-time for each fundamental property. So mass will change it one way, charge will have a different kind of warpage, and spin, etc. So if you've watched any kind of sci-fi movie, you've probably heard about force fields. Force fields exist in real life, but they're not what you see in a sci-fi movie. They don't block things, they don't provide a shield around things. Instead, physicists define force fields as the mechanism by which the space is warped or changed. It's the like perfume that's causing the stink to spread out from the object. At any point in space, any force field can be defined by the type of force field. So is it an electric force field? Is it a magnetic force field? Is it a gravitational force field? The magnitude, so how strong is that force field? How strong is the smell, if you will, from those objects with that charge? And also the direction of the force field, which way do they point? So force fields are going to be vectors, and we can use our vector map to deal with them. Here's an example of something called a vector map that shows the shape and magnitude of a force field, specifically the gravitational field around Earth. And we're going to talk more about what we see in those maps in the next slide. So the magnitude of a force field at any point in space is going to depend first, and this should make a lot of sense to you, but first it depends on how much of the fundamental property that object creating the force field has. So I guess I should say one thing at this point, which is that you don't need two objects to have a force field. We've talked about forces. You have to always have two objects to exert a force between them. You don't need two objects to have a force field. In other words, a single object can spread this stink by itself without any other objects nearby. So when we talk about the magnitude of the force field, all we care about is that single object that is causing the force field. And the more of whatever fundamental property that object has, so the more mass or the more charge the property has, the stronger the force field is. So the more of the perfume they spread out, the stinkier they are. If we are going to draw a vector field diagram of that force, you are going to indicate how strong this force is one of two ways, and you may see two different kinds of diagrams. Some diagrams indicate the strength of the force by the length of the arrows they draw in those vector fields. So you can see some of those arrows are longer than others. That means at that point in space, the magnitude of the force field is larger. Another way to show it is by making all the arrows the same size and indicating the strength of the force field by the density of those arrows. So like object A there, the arrows are not very dense. There's not as many arrows per area. And so we're going to assume that that is going to be a weaker field than object C, which has a lot of arrows. So you might see both of these kinds of diagrams in practice problems or on the exam. The other thing that hopefully becomes a little bit clear as you look at these pictures is that the magnitude of the field also depends on the distance of the object. And they're always stronger closer to the objects and weaker the further you get away, right? If I was stinky one way or another, you'd smell that stink most if you were close to me, and it would be weaker as you got further. So in that diagram that I just showed a second ago, right, obviously you can probably guess where the source of that field is, even though it's not shown in the diagram, because you can tell where the field is strongest, and that's probably going to be closest to the source. And in those other kind of diagrams, the density diagrams, right, you notice that even in a single diagram, that the density of the arrows changes as you move away from that source charge, and the spacing is close to the source charge, and then since the arrows are spreading out, the spacing gets further the further apart you get, the further away from the source charge you get. Force fields also have direction, as you've seen in those pictures, and the direction that we draw the force fields, like the way we point the arrows, has just been set by scientific convention worldwide. For objects that have mass, we're going to assume gravitational fields always point towards the source charge, or point towards the source of that field. So in this case, if we have a field map of Earth's gravitational field, you'll see that the field lines always are going to be pointing towards Earth. For objects with charge, though, it's a little different because we have positive and negative charges. So the convention says that we're always going to make our electric fields point towards a negative object and away from a positive object, source object. So you kind of need to memorize this. And another way, so you can see these are two equally charged objects. One is positive and one is negative. So they have the same magnitude of electric field. The arrows are the same density and length, etc. But for the positive object, the field is spreading out away. And for the negative object, we draw that field as coming in. Another way to view this, which is actually more productive as we move through, instead of thinking about the source object, because you can't always actually see the source object in some problems. Sometimes you just have the field and you don't care what object's causing it. We're going to care about the other objects that are in the field. And so another productive way to view this is if you imagine taking a tiny positive charge, like a single proton, and sticking it in space somewhere, the direction those arrows are pointing are going to show which way that positive object would move. Of course, you put a tiny negative object, it's going to go opposite, but those arrowheads are going to point in the direction that a positively charged object would move if they were put at rest at that point in space. For the electric field, we are often asked to calculate the strength of the field, and we are going to give that a new variable, big capital E. A little note, for gravitational field, the variable is little g, and that's the little g you've been using all year. So that little g is analogous to this big E as far as the field strength goes. But in any case, for electric field strength, we use capital E. The units of electric field strength are newtons per coulomb, or newtons for every coulomb. Gravitational field strength would be newtons per kilogram because it's a different fundamental property. But electric field strength is newtons per coulomb. And the equation for electric field strength just has two relationships in it. So there is a linear relationship between an electric field strength and the source charge magnitude. So the bigger the force charge, the source charge, the bigger the electric field is. And then there's actually an inverse squared relationship between the electric field strength and the distance from that source object, as we saw sort of earlier. So the equation for E on your AP equation sheet looks like this. Remember that thing at the beginning is Coulomb's law constant. It's little k, so you can write it out as E equals kq over r squared if you prefer. That saves a little bit of time. But the size of that whole piece is 9 times 10 to the 9th meters every second. I'm just going to put this in here one more time because this is a really common mistake people make. When you are calculating electric field strength, the Q in that equation is Q of the source charge, okay? Because sometimes you're calculating an electric field strength for an object and you have another object somewhere in play. And you got to make sure that you don't mix up which charges you're doing. Electric field strength depends entirely on the charge generating it. Therefore, it makes sense that the Q that we're going to use in this equation is Q of the source. Let's run through a quick example where we use that equation. Let's say we have a source charge, a big positive source charge, and I want to know what is the electric field strength at that location marked by the star. And I measure that that is 6 meters away from the point charge, and I know the magnitude of the point charge is 1.6 times 10 to the negative 8th coulombs. You should be able to use that equation from the last slide to calculate the electric field strength at the location of the star. So pause the video for a second and go ahead and run through that calculation. If you did it right, you should have gotten E is 4 newtons per coulomb at that location, and the direction, of course, is going to be outwards because that's a positive object everywhere at that same location. Small follow-up question. I now have a blue star at a location that's only 2 meters away from the source charge. What would the electric field strength there be? Hopefully you're not grabbing that equation again. You're thinking about this in terms of relationships, but pause the video and take a second to think about it. So because there's an inverse squared relationship, if I make my distance 1/3 as much as it was before, the electric field strength is actually going to get bigger by a factor of 3 squared, which is 9. So it gets 9 times bigger because there is an inverse squared relationship between the radius and E. So the electric field strength at that location should be 36 newtons per coulomb. What happens if there's multiple source objects exerting force fields all in the space around them? Well, if you have several objects that are creating force fields in the same vicinity, the field strengths can be added or subtracted at any point in those spaces to find sigma E, or the net force field strength at a point in space. We do this the same way we added vectors when we talked about forces and electrostatics a little bit earlier. A little bit of a note, this is why we have to be really careful knowing what direction these forces are, because fields in the same direction are going to add to each other to become a stronger field, and fields in an opposite direction are going to subtract or cancel each other out. You can even have a point in space where there is a zero field when you might have 2 or more other fields that are canceling each other completely. So for example, if I have an electric field from some object, and I'm not even drawing the source objects, I'm just telling you that the electric field strength at some point in space is 3 newtons per coulomb to the right, and I happen to know there's another electric field from some other source object that's 4 newton coulombs per coulomb to the right, and I want to know the total electric field at that spot. Sigma E at that spot should be 9 newtons per coulomb to the right, so you just add those vectors together. However, if those force fields were in opposite directions, so if the 3 newtons per coulomb was to the right and the 4 was to the left, then at that point in space, the electric field, the net electric field would be 1 newton per coulomb to the left, because we had 3 to the right, 4 to the left, we're left with 1 to the left. If you're really unlucky, they'll give you those force field directions to be perpendicular to each other. So if I have a force of 3 newtons per coulomb to the right and a second force that's 4 newtons per coulomb up, then the sigma E, or the total E, is going to end up being 5 newtons per coulomb. You can use Pythagorean theorem to find that at an angle of, as I've drawn it, 53 degrees north of east. And you can calculate that using your trig functions. So electric fields can be added the same way electric forces can be added. They're all vectors. Sometimes you see these more complicated looking electric field diagrams because we have multiple source objects in a location. The field diagram on the left there shows what it would look like if you had 2 negatively charged objects in the same space. So what you see there is all the field lines going towards the objects because they're negative. And in the middle, right, if you picture what a proton would be doing kind of in the middle, a positive test charge, it gets pulled by both of these objects, right? And if you put it right in the very middle between those 2 charged objects, if they have exactly the same charge, it wouldn't be pulled at all because it's being pulled equally in both directions. So the total electric field on it at that point is going to be 0, which is why you see that sort of gap right in the middle of that first diagram. Second diagram is for a positive charge and a negative charge in the same region of space, and the positive charge is always always repelling positive charges, and the negative charge is always attracting them. So at every point in space, we have an electric field. There's no places where we have 0. There's some places where that electric field is extra strong and extra dense. You can see in the region in between those charges, we get a really strong electric field because both of those forces tend to add together. Incidentally, the same is true for gravitational fields, which is kind of cool. You tend to think of Earth's gravitational field as being the dominant gravitational field around us, but if you move towards the moon's gravitational field becomes more and more significant, and there's actually a spot called the neutral point in between the Earth and the moon where there is no gravitation, no net gravitation, because the moon is pulling in one direction, the Earth is pulling in the other direction. So objects in that field experience true 0G. It's a very important scientific location, and every country on Earth is trying to stick satellites there all the time. So just kind of a fun fact. All right, so what do we care about? What are we going to use this for once we find the overall field strength at a point in space? Well, usually what happens then is we bring in a second object. Okay, so now we've got 2 objects, we can have forces, right? And so we're going to bring in the second object, and while we know from Newton's third law, forces are always equal and opposite, both objects experience force. Often in this unit, we are sort of considering things from the perspective of the second source, and we sometimes call it the test source because it's the thing we're testing, it's the thing we're interested in. Test object, test charge, it can be called any of those things. And so we're bringing in the second object and we're going to stick it somewhere that we have an electric field. So what would the electric field strength at that location tell us? It's going to tell us how much force that object experiences per coulomb of charge that object has. Okay, so that test charge, its charge matters too, just like with gravitation. We hold objects in the Earth's gravity field. The bigger they are, the more gravitation they feel. Same is true with charged objects. When you put them in electric fields, the bigger their charge is, the more force they're going to feel. But the field strength tells me how much force per charge it has. So for gravitation around Earth, it's 10 per kilogram, right? When we bring objects into Earth's gravitational field, it works kind of the same way. So there is an equation on your equation sheet that shows this relationship. It says E equals Fe over Q. That E on the left is the net electric field strength due to whatever source charges we had going on that we calculated on the last couple slides. Fe is going to be the force on the test charge, okay, and Q is the charge of the test charge. So this is the force per coulomb of test charge. And so in this equation, you've got to be really careful not to accidentally plug in the Q for the source. We used that in the last equation. This time it's going to be Q for test. However, and as I mentioned a minute ago, remember that all forces are interactions between 2 objects and they have to be equal and opposite. So when we calculate that Fe on the test charge, it's going to be the same as the force on the source charge. We just often don't really care about what's happening to our source charges. Let's run through a quick example of how we would use this equation. So here's an example of that source charge that we found the force electric field strength was 4 newtons per coulomb at a certain distance. And now we're going to bring in this little tiny test charge with a 4 coulomb charge to see what happens to it. So if I stick a teal object at a point in space where I already know that the electric field strength is 4 newtons per coulomb, the amount of force that that teal object experiences is 16 newtons. It's its charge times the field strength. And the direction of that force is going to be, for this object, because it had a positive charge, is going to be away from the source charge. Newton's third law says the source charge also experiences the same amount of force in an opposite direction. Now let's put a second object at the same distance from that source charge, which means that the electric field should be the same strength at that distance. But the second object has a charge of negative 30 coulombs. So that purple object is going to be experiencing more electric force than the blue object did because its charge is more, even though the field strength is the same. And specifically, it's going to be experiencing 120 newtons of force, the product basically of the electric field strength times its charge. And the other thing to note is the direction of this one is going to be towards the source charge. So that's all the negative sign tells me, is that opposites are going to attract. So we've got 120 newtons towards the source charge on that object. The last thing I want to mention in this video is a uniform electric field. Many industrial applications that use electric fields, which happens all over the place, depend on being able to create a region of space that has a constant or uniform electric field. So we're not getting stronger or weaker as we move away from a source. I want the field to stay the same strength everywhere. The way we do this is by getting two plates. So we're not talking about point charges anymore. We're talking about a plate, and we're going to charge them up oppositely. As you can see from this electric field diagram, if I have a positive plate on the top and a negative plate on the bottom, what you end up with is this uniform field going from the top plate to the bottom plate. The math behind why it's uniform is actually really interesting. We'll talk about that briefly in class, but for now, just take it for what I'm telling you, that it is uniform in the space in between those two plates. So this means that both the magnitude, so how strong the field is, and the direction of the field is uniform, no matter where you are. So if you're close to the top plate, if you're right in the middle, if you're close to the bottom plate, the amount of field strength is the same everywhere, which means that the amount of force on an object is the same everywhere, which means we have a uniform acceleration. So we're speeding up if we put an object in there, but we're speeding up at the same rate the entire time we move through that space. So those are really important properties of uniform electric fields. You may have noticed a little curved region on the side of those uniform electric fields, and that exists. It's called an edge effect, and it kind of looks like that electric field map we saw of the opposite charges. That's the curved part as you move further away from the center of the plates. All right, we've gotten to the end of the video, so please take a minute to revisit your essential question, which is, how do objects communicate their fundamental properties without touching each other, and all the specifics that we went into about electric fields. I also put a comic up there. I would replace girls in the last slide with maybe parents or younger siblings or whatever it is that's annoying you at the current moment, but I still thought the comic was funny. Thanks for watching.